Welcome to Analog Electronic Circuits. This is lecture 19 and we are going to continue from our what we did in the last class. So, we are going to continue with differential amplifiers. So, in the last class we had studied the differential amplifier and we analyzed the differential amplifier from a brute force point of view. That is, we analyzed it by using superposition. One at a time we applied the two voltage sources and found the outcome. Okay. Now, what I am going to do today is so that is one thing that we did in the last class. The other thing that we did in the last class was we replaced the load, that is the resistor on top of the differential amplifier, with a PMOS device, and that is called an active load. And the PMOS device is very nice because it behaves like a current source. So, at DC it provides just the right amount of current, whereas for the signal it provides a large resistance, which is exactly what you wanted, and that basically takes over the role of the resistor, and therefore, it allows for better swing hopefully. So, let us take a look at that, a relook at that structure, and let us try to understand the performance limitations. By now, I hope you understand that there is nothing special about PMOS devices. PMOS devices are just like NMOS devices. They are in fact the same as far as the small signal incremental picture goes. However, when you analyze it at DC operating point, then instead of taking source gate to source voltage, you take source to gate voltage. Instead of taking drain to source voltage, you apply source to drain voltage, that is all. Otherwise, there is absolutely no difference, just that the current flows backwards. Current does not flow backwards in the incremental picture. In the operating point, current flows backwards, that is all. All right. So, I want to point out that there is nothing special about the PMOS device, do not be afraid of it. A lot of you are genuinely afraid of the PMOS device. Whenever PMOS device pops up, you feel scared, should not be the case. So, there is a current source over here, this is called the tail current source. In reality, this current source is going to be made with a MOSFET, with a current mirror. Okay. So, these nodes that I have marked out, let us point out the values at these nodes. Let us first take some numbers. Okay. I like numbers. Okay. So, let us say I want to keep VGST as 0.2 volts. Okay. And let us say ordinarily the W by L of the devices is such that for this VGST of 0.2 volts, the current through the device, the current through this particular device, how much do you want to keep it? K times 0.04, K into VGST squared. Okay. So, let us keep it at you know what 100 microampere, 0.1 milliampere. Okay. So, K times 0.04 is 0.1 milliampere. So, therefore, K, which is mu Cox by 2 W by L, let us keep that as 0.1 milliampere by 0.04. So, that is 2.5 millisiemens per volt. Okay. So, if I keep mu Cox by 2 W by L as 2.5 millisiemens per volt, then the current through this, if I apply VGST of 0.2 volts, will be this times 0.2 squared, that is this times 0.04. Okay. So, that is 0.1 milliampere. Okay. So, I will choose, so there is some value of mu Cox by 2, I will choose W by L such that this is 2.5 millisiemens per volt. Is that okay? Fine. Now, I have decided what are the sizes of these two transistors. Size means W and L, W by L ratio, right. I would like the current here to be 0.2 milliamperes, and for 0.2 milliamperes I still want, I mean VGST of 0.2 volts is a nice clean number. Okay. So, therefore, I will choose W by L is equal to 2 times. So, let us say this is 1 time W by L, 1 time W by L, then this one should have 2 times the W by L of those. So, that VGST of this device is the same 0.2 volts. Okay. And let us say Vt is 0.5, in which case I need to somehow apply 0.7 volts over here. So, if I apply 0.7 at this node, then automatically that conducts 0.2 milliamperes. If it conducts 0.2, it splits up into 0.1 and 0.1. If 0.1 has to come this way, then this will develop a VGST of 0.2 volts, that is VGS of 0.7 volts or so. But I do not know the source voltage. This source voltage can be anything, right, anything more than 0.2, because this needs to be in saturation for it to behave like a current source. Okay. If this is in saturation, then VGS minus VT 0.2 volts, right. So, VDS has to be more than 0.2 volts. If VDS is more than 0.2 volts, then that means this node over here has to be greater than 0.2. All right. That sets a lower limit for both of these nodes at how much? 0.2 plus another 0.7. So, this node has to be greater than 0.9. Okay. Anything larger than 0.9 seems to be all right with us. Any questions? Okay, great. Now, we will see, we need to also work out how much larger can it be. Can it be, we have not yet decided what is going to be the voltage here. Let us say the voltage here is, you know what, let it be 2 volts power supply. By the way, how will you generate this 0.7? Will you apply a voltage source of 0.7 volts here? Will you? No, no voltage sources. Okay, only one battery is allowed, 2 volts, that is it. You will have a 0.1 milliampere current source or a 0.2 milliampere current source or any other current source, reflect it with a current mirror and generate 0.7 volts. That is how you will do it, not with a voltage source, never. Is that understood? Okay. Okay. So, this is not a voltage source, this is coming from somewhere. Let us get that clear in our head. Okay. Right now, it appears that I have put a number over there, it appears like it is a voltage source, it is not a voltage source at all. it is coming from something else. Okay. Current is being pushed into this device, that is generating a diode voltage, right, and how much current will decide what is the size of this diode, because you want VGST of 0.2 volts for that diode. Okay, and that is how you are going to generate 0.7. Why are we doing this? Because VT changes with temperature. Okay, you think VT is 0.5 volts, it need not have been 0.5 volts. If it was 0.4, even then this will work. But if you apply 0.7 volts and VT is suddenly 0.4, then suddenly now you have got different currents all over the place, your currents are all wrong. Okay. So, you are always going to bias it using a current mirror, not with voltage sources. All right. Now, what next? What about these two PMOSs? These two PMOSs also need to conduct 0.1 milliampere at DC. Okay. And for 0.1 milliamperes, VSG has to be more than VT by a certain amount, okay, according to the K of the PMOS. So, let us say usually mu of the PMOS, usually what happens is that Cox of the PMOS is the same, Cox of the NMOS and Cox of the PMOS are equal usually. Okay. Mu of the PMOS is usually much lower than mu of the NMOS, and this much lower could be a factor of 2 lower, it could be a factor of 3 lower. However, in modern nanometer technology nodes, it is not necessarily lower, it could also be equal or even higher sometimes. So, this PMOS mu of the holes versus mu of the electrons. Mu of the electrons is the mu in the NMOS, mu of the holes, the mobility of the holes is this parameter in the PMOS. Okay. So, in the PMOS the mobility is usually lower, holes are usually less mobile than the electrons. However, it so happens that in very fine technologies, modern technologies, 28 nanometer, 22 nanometer, 14 nanometer, it so happens that the whole mobility is more or less at par with the electron mobility and sometimes even higher. Okay. In older technologies, the whole mobility is substantially lower, 3 times lower, 2 times lower, something like that. So, it all depends on which technology you are using, where you are, and we are not going to discuss the physics of the mobility. So, do not ask me questions, why is do not ask me. So, this is out of the scope of this particular course. We will take a value and deal with that value. So, let us say, let us assume that the whole mobility is 2 times smaller than the electron mobility, in which case this mu Cox by 2 is half of the NMOS mu Cox by 2. Okay. Suppose, in which case to have 0.1 milliampere with a VGST, that is VSG minus VT, right. So, we should actually call it VSGT for the PMOS. So, VSGT of 0.2 volts, if you want that kind of a source to get voltage, then this device requires a size of 2, W by L should be 2 times the W by L of the original, because the whole mobility is half of the electron mobility. Okay. So, it all depends. So, if the whole mobility is 3 times smaller, then this would have been a number 3. If the whole mobility is 1.5 times smaller, this would have been a number 1.5, and so on. Okay. All right. In such a case, we will get 0.2 volts of VSG minus VT, if you once again say that V t is 0.5 volts. So, the V t of the PMOS is different from the V t of the NMOS normally. They are not related to each other, however, they might be of similar values. So, if V t of the PMOS is also 0.5, then that means that I need a drop of 0.7, VSG has to be 0.7, which means this node has to be at 1.3 roughly. Okay, and it all depends on all of these various assumptions that we have made in our calculation. Now, how are you going to make that 1.3 volts? With a voltage source, with another battery? No, no, right? I hope not, right? Do not use batteries over here. You are again going to use a current mirror. You are going to draw exactly the same amount of current through another PMOS, and that is going to mirror it. Okay. So, this is something that is not being drawn right now, because that is not our focus, right. Our focus is not over here. You are going to somehow generate the 1.3 volts, not with a voltage source, certainly not with a voltage source, not with a resistive divider, not with any of those techniques. You are going to use a diode connected MOSFET, pull a current through a diode connected MOSFET and generate the right voltage. Fine. Okay. Now, the question is, what is the maximum voltage over here? What is the swing? What is the maximum swing at the two outputs? What are the maximum and minimum voltages at the two outputs? So, what is the maximum voltage? Maximum voltage at which these PMOSs still behave like a current source. Okay. As long as the PMOSs behave like a current sources, you will get gain in the amplifier. Okay. So, the voltage at which the PMOS still behaves like a current source is 1.8. Why? Because VSG minus VT was 0.2 volts, that is what we had chosen, right, and therefore, V source to drain, not drain to source, has to be more than 0.2, which means if the source is at 2 volts, then the maximum tolerable voltage at the drain is 1.8. Okay, and whatever is happening on this side, the same thing will happen on the other side. Okay. Is this okay? Fine. So, now I know that the maximum voltage here is 1.8. Is there a minimum? If I lower the voltage, the PMOS is happy. So, we do not look at the PMOS. Who is going to start feeling unhappy if I lower this voltage? The constraints are now going to come from the input device as well as the tail current source. Okay. These three devices will start becoming unhappy if I lower the voltage, okay, at the output. All right. So, what is the minimum voltage? Okay. So, it depends on the input. So, the minimum voltage now starts depending on the input voltage. Input voltage, I just said it has to be greater than 0.9. Okay, I have not declared a maximum of the input voltage, but you see this to keep the input device in saturation, VDS of the input device has to be more than 0.2, because VGS minus VT is 0.2. So, if I want to keep VDS of the input device more than 0.2 and the gate is at a certain voltage, then that means the drain, the lowest voltage at the drain is the gate voltage minus VT. Do you see my point? If this is at 0.9, suppose if this is at 0.9, this is at 0.2, Okay. Then the lowest voltage over here is 0.4, but this is not necessarily at 0.9. If this is at 0.9, this is 0.4, which is 0.9 minus 0.5. Okay. Suppose this was 1.2, this can be any voltage greater than 0.9, right. You are saying that I do not know what the gate voltage is, it can be anything that is coming from the input. The input can be anything more than 0.9. Suppose this input is 1.5 volts. Okay. If the input is 1.5, then what is going to be the voltage at the source? 1.5 minus 0.7. Okay. So, 0.8 at the source. Now, if the source is 0.8, then the lowest voltage at the drain is 1, okay, which happens to be gate minus 0.5, gate minus V t. Okay. If the input difference of the two inputs, let us say, is small v in, that is my input differential signal. If the difference between the two inputs is small v in, this is the plus terminal, this is the minus terminal. The operating point voltage over here is capital V in, capital V in, all right. So, then this voltage is capital V in plus V in by 2, this is capital V in minus small v in by 2. Is this fine? So far so good? Now, I do not know the value of capital V in, it can be anything more than 0.9. Okay. What is a voltage at which this minimum and the maximum are equal? Could it be that the minimum and maximum are equal? Basically, there is no condition. In such a case, there is going to be no condition, there is going to be no swing at the output. Output cannot, I mean, there is no condition at which both the top device as well as the bottom device are in saturation. Could it be? Could it be that the maximum and minimum are equal? In that case, V in is 2.3 volts. Okay. So, for example, if this is at 2.3, if capital V in is 2.3, then what happens? This is at 1.6. If this is at 1.6, then the lowest voltage over here is 1.8. Okay. The highest voltage over here is also 1.8, which means that if I apply any signal at the input, one of the two devices collapses, it is all gone bad. All right. So, there is no flexibility at the input. You can't really apply a signal at the input and hope that the amplifier works. Okay. So, this capital V in has a maximum as well. So, it is limited in terms of range, limited from the top side, limited from the bottom side. If it is too large, then there is no output which will satisfy saturation of all the devices. Okay. If it is too small, if this voltage is too small, then the current source below is going to collapse and not behave like a current source. Okay. So, this is the constraint at the two inputs. The input is constrained, not just the output. Now, depending on the voltage, the actual voltage at the input, the actual operating point voltage at the input, depending on that, I get a swing at the output. All right, is this understood? So, the output swing limit actually depends on the operating point at the input. All right. Now, this operating point is not necessarily a constant value. This could also be a common mode signal, a common mode, an interference. So, this capital V in over here, right now I have written it in capital letters indicating that it is a static value. Okay. But does this have to be static as long as these two are equal? That is, can this be an interferer? Can this be a common mode interferer? Can it be a sine wave, both moving together? The answer is yes, it could be a sine wave, okay. But if it is indeed a sine wave, then it should be in this range. Okay, whatever happens over there, whatever it is, right, whatever that common mode signal is, interferer is, it should be within this range, because outside these bounds the amplifier collapses, does not amplify anymore. It does not amplify the differential input anymore. All right. So, this is called the input common mode range. Input common mode range. In short, it is called ICMR. Okay. So, this is the input common mode range. So, for this range of input common modes, this amplifier is actually going to amplify. If V in is more than 2.3, then there is no output at which things are in saturation, and if V in is less than 0.9, then once again the tail current source is outside of saturation, and things are not really working. Okay. So, this is called the input common mode range. This is the DC operating point value at the input for which the amplifier is going to work. This is not the input signal range. This is not telling you what is V in, small v in. Okay. This is not, this has nothing, no bearing on small v in. Okay. This is, we are only talking about capital V in. Okay. And we said that capital V in does not have to be a static value, it could also be something which is changing with time. In any case, that whatever is changing with time, that is an interferer, and that will be rejected, right. That rejection ratio is called the common mode rejection ratio, CMRR. Remember, we discussed this. Yeah, CMRR, ratio of common mode differential mode gain and common mode gain, right. How much is signal to interferer at the output versus how much is the signal to interferer ratio at the input. All right. So, that is how much you are rejecting the input common mode signal. So, this input common mode does not have to be a static value. Okay. What is the input common mode? It is the average of these two inputs. The average of these two inputs right now looks like capital V in. Okay. And capital V in therefore need not be a static signal, it could be something which is changing with time. And how much can it change? This is the input common mode range. Okay. As long as the input common mode changes within this range, I will be able to reject it. Outside of this range, the input common mode, the amplifier will no longer behave like an amplifier, which means that all kinds of other things are going to happen. Differential gain is going to become much smaller, right. Common mode gain is probably going to become larger, in which case signal to interferer ratio at the output by signal to interferer ratio at the input is no longer going to be large, right, in which case the common mode signal will propagate to the output. So, all kinds of bad things are going to happen outside of this range. Within this range, the amplifier will behave itself. Is this all right? Is this discussion okay? So, this has no bearing on small v in. How big or small v in can be, we are not talking about it. Okay. We are not talking about the difference, the actual swing at the output. The actual swing at the output is related to the value at the input right now. Okay. Whatever I pick a value capital V in of capital V in, accordingly the actual swing at the output, the actual swing limits at the output will change. Okay. It all depends on what is the actual input common mode value. Is this okay? So far so good? All right, great. So, this is an important discussion. All right. A lot of people want an amplifier. So, ideally you are trying to make this amplifier, right. This is your something that you are aware of. This is the op amp, right. Your the objective of this course is to make this op amp, this amplifier, where the output is proportional to the is a large gain times the difference between the two inputs. This is what you are trying to make. Now, this object is not going to be ideal. It is not just proportional to the difference between the two inputs, right. There are constraints on the actual values of the two inputs. What is that constraint? The average of the two inputs has to be within this range, the ICMR range. Okay. Otherwise, the difference of the two inputs is not going to be amplified. So, for example, if my two inputs over here are 0.5 volt and 0.6 volt, then this amplifier is not going to amplify the difference, even though this is 0.5, this is 0.6, right. This device is now out of saturation. So, this difference of 0.1 is not going to be reflected in the true sense at the output. So, I apply 0.5, 0.6, I expect this op amp to work, it is not going to work, because there is a range of inputs for which it will work. There is an input common mode range. So, ordinarily when you are designing an op amp, if you are going to planning to design a good op amp, then you want this input common mode range to be as large as possible. Okay, that has not happened over here. That has not happened over here, because this device went out of saturation, all kinds of bad things happened, right. We do not know. This has a lower limit, this also has an upper limit. Fine. Are we going to try to solve the problem? No, we are not. Right now we are not. Right now we are just exploring circuits. So, this is one circuit that we explored. Okay. Right now I am not going to even attempt to solve the ICMR range problem, right. We are not going to do it right away, we will do it later on. Okay. So, there is one more strategy, right. So, as you see, when you are trying to make an op amp, the output, if you are trying to make the output could be single, the output could be double, right. So, you could have two outputs, you could have one output. Ordinary op amp has only one output, right. So, you do not really have to make two outputs like in this circuit. So, this circuit had two outputs, you do not require two outputs, just one output is sufficient. Okay. So, one other possibility is, can we modify this op amp and get some benefit if I have only one output as opposed to two. So, now all I am saying is I am not interested in two outputs, I am interested only in one output. Okay, I can pick either one. I have picked this one today. Okay, today I have picked this one, tomorrow I might flip over to the other side, it does not matter. So, only one output in the op amp. Can I make some changes and take advantage? And the answer is yes, you can. Okay. Why not put a current mirror instead of two current sources? Why not put a current mirror on the load? Okay. So, this is my plan. What is the plan? The plan is this is some current I naught, this is I naught by 2, I naught by 2, and then whatever this current is I naught by 2, that gets mirrored by the current mirror and I get I naught by 2 over here. All right. And that way you know, remember in the earlier circuit you had to create this 1.3 volts, right. This way I do not have to create that 1.3, it is already self created, it is self biased, the load is self biased. I just have to create this particular voltage, which I do with a current mirror from outside. Some reference current with a mirror, I create that I naught. Okay, the rest of it is self biased. Is there any advantage to this? Well, there is. Think about it. So, if let's assume that this node is a constant fixed voltage. Okay. Remember when we talked about differential circuits, you did the half circuit and then the midpoint of the half circuit, if my two inputs are anti-symmetric, that is plus delta V and minus delta V, then the node in between does not move. Okay. So, let us assume that the node in between does not move. Here this circuit is no longer symmetric, right, the symmetry is broken. One half is no longer the mirror image of the other half. Okay. So, really I can't apply that same principle over here, but let us assume that I apply delta V or small v I apply and minus small v I apply on the other side, and this node let us assume does not move. Now, if this node does not move, then this current is going to be G m times V. This current is going to be G m times V, and then on top I have got a current mirror. Now, the current mirror not only mirrors the DC, the operating point current, it will also mirror the signal current, right. So, this current is now G m times V. So, therefore, this current is also going to be G m times V, which means that 2 times G m times V is going to be pushed out onto the load, okay, and the load in this case is nothing but the combination of RDS of the NMOS and RDS of the PMOS, okay, as long as you have not really placed an actual load. If you place an actual load, then fine, but if you do not place an actual load, then it is RDS of the PMOS in parallel with RDS of the NMOS, and therefore, the gain of this circuit is 2 times GM times RDS of PMOS times parallel with RDS of NMOS. So, you get an extra factor of 2 in the gain. Earlier what was happening? Earlier this connection was not there. I naught by 2 biased from outside. Okay. I had plus V over here minus V over here. So, when I had plus V, this was static. So, this created GM times V. GM times V came through that load and created a voltage. Here I had GMV going the other way. Okay. If you think that this is a current source, then it goes out into the load. Okay. If you think of RDS, then that GM times V times RDS of the PMOS in parallel with NMOS gives you the voltage at this node. So, the voltage at this node is something, the voltage at the other node is minus of that something, and that something is GM times RDS of PMOS in parallel with RDS of NMOS. So, one is plus, the other is minus, difference is 2 times. Okay. Here this one, forget it, this current whatever is happening, whatever signal current goes through gets reflected on the other one, 2 times GMV gets pushed out into the load, which is RDS of PMOS in parallel with RDS of NMOS, and therefore, you get the same as the difference in the earlier case. In the earlier case, you got a differential output of 2 times GM times V times RDS of PMOS in parallel with RDS of NMOS. Now, just this voltage is 2 times GM times V times RDS of PMOS in parallel with RDS of NMOS. All right. So, clearly there seems to be an advantage. Okay. Seems to be. We have to analyze it nicely, right. There is some scope in this circuit. Clearly, this is a circuit that has potential. All right. So, this is called the self biased active load differential amplifier. Okay. So, the active load is self biased basically with a current mirror, okay, and it is differential input, single ended output. So, this is what we are going to study next. So, this is going to be our agenda right now. So, let us study it in a little more detail. Okay. So, my two inputs are some common mode or some DC operating point plus V in by 2 and the same DC operating point or common mode minus V in by 2. Okay. And in the small signal, there could be a small signal part in this, right. The common mode interferer is a small signal. So, potentially there is small signal here, but this is an open circuit in the small signal. Okay. In that case, whatever current comes this way has to go up the other way. Whatever the current comes this way has to, it has no choice, this is open circuit in the small signal. Let us assume it is open circuit, okay, and not just a MOSFET. Let us assume it is a good current source over here, in which case whatever current comes this way has no choice, it has to make its exit the other way, nothing doing. Okay. And then if you assume this is a good current mirror, then whatever current comes this way has to be mirrored the other way, and therefore, the net output current is 2 times this current, the current created. So, you have got some circulating current. So, if I create I over here, this is also I, this is also I, and this is I, which means 2I goes out into the load. This is our analysis right now. Okay. Let us see. Let us assume the voltage over here is something, some in the small signal. Let us assume the voltage here is V x. Okay. So, if this voltage is V x in the small signal, then what is I? So, let us call it some common mode signal. Now, this is I, and minus I. So, I is going the other way for this particular one. All right, this is okay. So, GM times, so what are your unknowns over here? Your unknown is Vx and I. These are your two unknowns. The knowns are Vcm and Vin. Okay, you have applied Vcm and Vin from outside, and the circuit responded by creating a Vx and generating an I. Okay, and I want to know what is the value of Vx, what is the value of I. What are they? So, you have got two equations, I equal to so much and I equal to so much, and this is equal to this. Okay, two equations, two unknowns. So, first of all, you have got this one equation where you have got Vx as an unknown, and therefore, Vx can easily be computed. Okay, Gm times so much is equal to Gm times so much, cancel out Gm, right. That automatically tells you what? Vx has to be equal to Vcm. Okay, Gm cancelled out, in which case this voltage over here is equal to this voltage over here. V in by 2 politely cancels out. Vcm, you get 2 times Vcm is equal to 2 times Vx, and therefore, Vx has to be equal to Vcm. Okay, so, you have got no choice, Vx has to be equal to Vcm, Vx has to be equal to Vcm, and therefore, VCM minus VCM is all 0, VCM minus VCM is all 0. So, I is nothing but GM times V in by 2. So, I applied VCM plus V in by 2 over here, VCM minus V in by 2 here. Vx was the same as VCM. Okay. Just by the way, we assumed over here that the signal current through this current source is 0. Okay. Is that correct? If this current source was not ideal, if there was a resistance here, what would be the signal current? The signal current would be VCM by the output impedance of the current source, right. So, that would not be correct. However, VCM is an interferer. If I say that there is no interference, if I assume that the interferer has already been gotten rid of, suppose, okay, suppose the interferer is already not there, then this signal current is actually 0. So, if VCM happens to be 0, this signal current is actually 0. In the other extreme, if I make a very good current source over here, then I can tolerate interference, right. If I make a really good current source, then this element completely disappears. All right. So, I over here is nothing but GM times V in by 2. That is the signal current I. The same current follows through, it can't go through the current source. So, it follows through. Okay. And then what is going to happen? Then there is my current mirror over here, all right. So, the current mirror needs to mirror the current. So, if I pull I equal to GM, if I pull some I current through the current mirror, what is going to happen? What is going to be the voltage at the gate? So, suppose this PMOS has some GM. Okay, suppose this PMOS has some GM. All right, this is the diode connected PMOS. Diode connected PMOS means we have studied a diode. The MOSFET has GM, the MOSFET has RDS or GDS, whatever you want to call it. Okay. In which case the impedance looking in over here, right, if I draw current I through this MOSFET, then the voltage here is going to dip by a certain amount. How much is that? What is the resistance of this? The resistance of this is 1 by you have forgotten everything. Okay, you want me to do this? All right, let's first of all, you are not comfortable with PMOS, you are all groaning about the PMOS. Okay, fine, let us draw it with an NMOS. It is the same thing. Okay, the PMOS and the NMOS have no difference. All right, so do not worry about it. So, let us look at an NMOS. Okay. Now, to find the impedance of this circuit, you can do it in two ways. You can push a current, measure the voltage, or you can apply a voltage, measure the current. Both are okay. Which one do you want to do? Let us apply a voltage and measure the current. Okay, so, let us apply a voltage V here. If I apply a voltage V at the gate, then Gm times V current is pulled through the drain, but also remember there is an RDS from the drain to the source. I have applied V voltage across that RDS, which means that that will also create a current, a drain current. So, the net drain current is GDS times V plus GM times V, which means if I applied V, I get a current of so much, all right, and therefore, the resistance is 1 by GM plus GDS, V by I. Okay. So, let us hammer this in your head. Okay. Approximately this looks like 1 by GM. So, whenever you have a diode connected MOSFET, its approximate impedance is 1 by GM. If you want to be accurate, then it is 1 by GM plus GDS. No, GMB is not playing a role over here at all, because the body is ground, the source is also at ground, small signal ground. So, GMB is not doing anything. Okay. So, the impedance of this MOSFET is, of this diode connected MOSFET, is 1 by GM plus GDS. I pulled a current I, and therefore, the voltage over here has to drop, because I am pulling the current out. So, the voltage over here is going to drop by current times the resistance. Fine. Now, this same voltage is being applied to another MOSFET. This same voltage is being applied to another MOSFET. How is that one going to respond? This is the voltage over here. I have given the voltage, value of the voltage. So, this MOSFET is going to try to push a current which is GM times this voltage. Okay. So, the current that is being pushed is nothing but GMP by GMP plus GDSP times I. So, I am pulling a current I through this MOSFET, it responds by dipping this voltage. Okay. Now, when the voltage has dipped, the other one tries to push a current which is GMP times the dip. So, this is not really I, this is I times GMP by GMP plus GDSP, if you want to be accurate. All right. And now, you sum the two currents, you have got I and the other one, and this sum, which is almost 2I, but not exactly, is going to be pushed across the Norton equivalent impedance, right. Remember, this did not move. So, the Norton equivalent impedance is RDS N in parallel with RDS P, and that will create a voltage. Okay. So, let us stop here, and we are going to discuss further, maybe analyze this circuit in even more detail. A lot of you are unhappy about this analysis, right, you do not like it, fine. We will analyze it in more detail in the next class. Thank you.